There is a dominant philosophy driving Silicon Valley right now. Leaders like Sam Altman describe artificial intelligence as a self-reinforcing engine, a techno capital machine. Feed it enough data, energy, and compute, and it scales into a digital superintelligence capable of solving virtually any civilizational problem. But if we look at the macroeconomic data, that grand vision collides with a stubborn reality. Despite massive worldwide deployment of generative AI, aggregate national productivity has not experienced the promised explosion. Economists call this the new solo paradox. We see the technology everywhere, but the massive economic gains are missing because current AI mostly performs narrow, task-level automation. It helps write an email or summarize a document, but it rarely orchestrates the complex, dynamic workflows required to transform an entire industry. No matter how many gigawatts of power we pump into a multi-billion-dollar facility, raw digital intelligence remains economically inert as long as its potential is isolated inside a server rack. To actually impact human lives, these algorithms have to step outside the digital void and interact with a physical world that is strictly governed by unbreakable scientific laws. Even the software itself is bound by thermodynamics. According to a principle called Landauer's limit, the process of deleting a single bit of information permanently increases environmental entropy. You cannot erase digital data without releasing a precise, unavoidable amount of physical heat. Then there are biological limits. If an AI proposes a cure for a disease, it must be tested in living cells and human clinical trials. A supercomputer might think 1,000,000 times faster, but it cannot force a biological cell culture to divide any faster than its natural rate. Intelligence cannot override thermodynamics or fast-forward biology. To actually drive progress, artificial intelligence has to strategically navigate around these physical walls. This brings us to a more pragmatic alternative to infinite scaling. Anthropic's Dario Amodei describes powerful AI not as an omnipotent god, but as a country of geniuses in a data center, a highly targeted tool used to resolve specific scientific bottlenecks. We can see this working right now in the life sciences. Deep learning architectures like AlphaFold 3 are shifting structural biology from a slow observational discipline into a highly predictive science. Researchers at In Silico Medicine used an end-to-end AI platform to analyze patient data and isolate a specific enzyme responsible for a fatal lung scarring disease. Then, the system computationally generated a brand new small molecule designed to lock directly into that enzyme and neutralize it. Identifying a target and designing a lead molecule traditionally takes 5 to 6 years of expensive trial-and-error laboratory experiments. The AI pipeline completed that exact preclinical phase in 18 months, leading straight to a successful human clinical trial. The system does not break the biological speed limit. It simply calculates the correct clinical path in advance, bypassing years of physical dead ends. The same approach is accelerating the transition to renewable energy. Historically, discovering stable inorganic crystals required tedious manual testing. Google DeepMind's Genome Initiative bypassed that physical bottleneck entirely, computationally predicting 380,000 highly stable new materials for solar cells and solid-state batteries. In meteorology, an AI model called GraphCast mapped the Earth's atmosphere as a giant spatial network. It accurately predicted the exact landfall of Hurricane Lee in Nova Scotia, days before traditional physics-based models caught up. Yet, these systems have a known blind spot. Because deep learning relies entirely on historical training data, models frequently underestimate the intensity of extreme, record-breaking weather anomalies that they have never seen before. AI operates as a high-speed engine for pattern recognition, but true climate resilience requires coupling that digital prediction directly with traditional, physics-based science. In developing economies, the physical constraints are often a lack of basic infrastructure. To incorporate highly volatile renewable energy into municipal power grids, operators in India use predictive algorithms to forecast solar irradiance and dynamically balance the supply against real-time demand. Similarly, millions of smallholder farmers lack access to physical agricultural experts. Using mobile diagnostic platforms trained on hundreds of thousands of images, they can photograph a dying crop and receive an offline diagnosis and treatment plan instantly. Far from the elite corporate laboratories, The most immediate value of digital intelligence lies in operating as a decentralized force multiplier for existing human labor. Even when we successfully bridge the digital and physical worlds, we run into a sociological wall. In education, platforms like Conmigo and Duolingo Max offer highly personalized one-to-one AI tutoring at a massive scale. But giving a student access to an infinite tutor does not automatically guarantee they will learn. Educational researchers have identified a metacognitive gap. Struggling students often lack the self-regulation to focus, and they don't know how to formulate the right questions to ask the machine. To solve this, developers are pivoting away from passive chatbots. They are building proactive systems that interrupt the student upon detecting an error, and pairing those systems with human teachers to guide and sustain the student's engagement. We can scale computational reasoning to infinity, but human psychology and behavioral resistance remain the hardest constraints to overcome. This chart shows a framework from the Flourishing AI initiative. It maps an entirely different way to evaluate frontier models, measuring performance not by coding benchmarks, but by human-centric dimensions: character, meaning, relationships, and health. When tested against these holistic standards, today's leading models fail to reach the 90-point baseline for human flourishing. They offer highly capable technical processing, but often default to generic guidance that lacks deep moral or cultural coherence. Superagency represents an operational state where AI is strictly subordinated to human values, designed to amplify human decision-making rather than acting as an autonomous master. The optimistic case for artificial intelligence requires abandoning the fantasy of infinite, unconstrained software in favor of the messy, integrated reality of the Techno-Humanist synthesis.